When I'm not teaching, I like to build houses, other fun things like that. And I've got a little jack. It's called a bottle jack because it's kind of shaped like a bottle. And I've used this bottle jack, in fact, to lift up a good section of a house. So the idea is there's this part here that can come out of the bottle jack. And if you go back and forth with this, you pump a hydraulic fluid, some kind of oil in here, and it causes this piston to move up. And then if you put a house up here, let's say it's a red house, this is not to scale, but you can then lift up the house and you know, put something underneath it or something. I don't know why you'd need to lift up a house, but sometimes you do. So this bottle jack can lift up the entire house, although I can move this with my hand. Is something cool with mechanical advantage? Yeah. The reason that we get a mechanical advantage here comes from fluids. So I'd like to kind of draw a schematic of the bottle jack. The idea is that we've got a tube of some fluid. In our case, it's going to be oil. And the tube is very narrow here. But over on this side, it's freaking enormous. This one enables you to lift up cars and stuff also. So let's see, I'm going to write the pistons as a blue so that you can see that they'll maybe be able to move. Here's a piston that we could put over on this side. And here's a piston that we could put over on this side. And that sucker will be able to go up and down. If we push on this one down, then that one will go up. If we push on that one down, then this one will go up. And I'd like to kind of investigate the pressures of these things. Let's notice first that the area of this side, we'll call it area 1, is much, much, much smaller than the area of this side, which we'll call area 2. So here we go. Area 1 is much smaller than area 2. And we can get some equations going here. If this thing moves a little bit, we can call its motion d1, the distance that it's moved down, and then this one will move just a tiny bit up, and that'll be d2. And I'm sort of implying that these aren't the same distance. Is that reasonable? You know that volume must be conserved. If this is an incompressible fluid, then we know that volume is conserved for incompressible fluids. Sorry, that's 2 words there. Volume must be conserved. So the change in volume of side 1 is equal to the change in volume of side 2. So if side 1, I'm just talking about magnitudes, this is going to be the area of side 1 times how far it has gone, and this is going to be the area of side 2 times how far side 2 has gone. Of course, that's volume for these cylinders. So we can solve this for the distance. Let's solve it for distance 1, the distance that this piston needs to move to make that piston move a little bit. Well, it'll be something times d2, and that d2, that coefficient is a2 over a1. Notice a2 over a1 is this enormous number. So in order to move this piston just a tiny bit, you need to move this piston a ton. But what's the point of all this? The point is the force hugely bigger where? Where is the force hugely bigger? Which side? Pause. Okay, you're thinking that the force is hugely bigger on this side because the pressures are equal. P1 equals P2 because they're both the same fluid and they're at the same height, so we don't have any rho GH going on here. The pressures are equal, so the force of 1 times the area of 1 is equal to the force of 2 times the area of 2. And if I were to solve this for the force of 2, that might be the car that you're lifting up, right? The force of 2 is going to be, well, it's the force of 1 times area 1. Oh my goodness. Yeah, that's all wrong. So let's try this right. Pressure is force divided by area. Force of 1 divided by area 1 is force of 2 divided by area 2. Now I want to properly solve this for the force on side 2, lifting up our car, and I find this to be A2 over A1 times the force on side 1. And A2 over A1 is this, again, this enormous number, because area 2 is really big, area 1 is really small. Look, it's the same ratio as here. Look at these two equations. They're very similar, but they're kind of inverses in one another. Now look, you know what force times distance is. Why, that's work. So assuming no friction, the work that you do pushing this one down is equal to the work that you do pulling that one up. Aha! Which implies that it's a machine and its efficiency is 1. Now, of course, because it's viscosity that's going to be causing a little bit of heating up, there are little bits of this that interact with the surface and interact with each other that are going to cause it to heat up. Of course, it won't be perfectly efficient, but you can see that there's a force times distance thing going on here. So let's summarize this in just a moment. Let's try to be clean about this. I'm saying that we can get, by pushing a small force right here, we can get an enormous force up right here. So I can lift up a car by pushing down with my finger. Unbelievable. But I'll have to push down with my finger a really, really, really long distance. So it's like using that winch that we've got in the back of the room. I suppose there aren't any surprises about that. But the payback is this distance. You have to push the distance really, really long. So there we are. Let us, I'll go to the next bit in a different video.